Good afternoon. Welcome to week 7 of the NPTEL course on applied optics being offered by IIT Roorkee. So, we have successfully completed 6 weeks up until now. This is the 7th week. So, we are halfway through and 6 more weeks to go. That would complete this 12-week course. So, in this week 7, we were introduced to the concept of diffraction and in particular Fraunhofer diffraction, which is basically the far field effect. And in Fraunhofer diffraction, we studied a few simple cases. For example, the single slit diffraction, the double slit diffraction, and the multiple or the n slit diffraction. So this was the focus for week 7, and the assignment also basically is based on these topics of diffraction. So let us begin with the first question. So in this assignment, actually, we have more theoretical kind of questions, like some verbose kind of questions. Not really so many numericals out here. As you can see, most of the questions are like statement based questions. Very few numericals, if at all any. But I would show you some simulations of the diffraction effects so that you can. Okay, you are not able to hear me. Okay, wait, let me check. Hello, am I audible now? Okay, let me check what is wrong. Shweta, I see that you have not connected your audio. That's why you are not able to hear me. So if you could please connect to your audio. Okay, am I audible to all of you? If you could write in the chat box if I'm audible or not. Someone just mentioned that the person was not able to hear me. So can you hear me? Yeah, okay, fine. So Lokesh is saying yes, he can hear me. So for others who are not able to hear me, I would suggest going to the YouTube channel. So just give me a second. I will provide the link to the YouTube channel. So that's the link to the YouTube channel. And those who are unable to hear me can visit on the YouTube channel and watch the video over there. Let me put that in the chat box. I hope that should solve the problem. Yeah, it seems only Shweta is facing this audio problem. So I see, Shweta, actually you have not connected your audio. So that is the problem. Okay, so with that being sorted, let us come back to our assignment. So once again, let me just start from the beginning, since some of you joined late and since it seems that there was probably some audio issue. So this is the week 7. So we will be discussing week 7 assignment problems. And the deadline for week 7 assignment is sometime in the next week. So you do have a few days in your hand. And so basically 6 weeks have been completed. We are halfway through and 6 more weeks are there because this is a 12-week course. And in this week, the topics that we looked at were based on diffraction. To be precise, Fraunhofer diffraction. So when we say Fraunhofer diffraction, it means the far field regime. So if I were to basically summarize this week. So in this week, we looked at Fraunhofer, meaning far field, Fraunhofer diffraction. That was the focus of this week. And when I say far field, that means that the source and the screen both are kept at infinite distances from the slit. So even the source is at infinity in comparison to the slit, and the screen is also at infinity in comparison to the slit. This means that we assume that plane waves are hitting the slit, and after hitting the slit you go very far away from the slit and then look at the pattern. So when we say infinity in physics, infinity implies basically much larger than the length scale in question. So over here the length scale is the slit width. So when your distance is much larger than the slit width and the wavelength, of course, the wavelength of light, then you say that you are in the far field regime or the Fraunhofer regime. So that is what one means by far field. And the other example of diffraction, the other regime of diffraction is the Fresnel regime of diffraction. Fresnel meaning near field diffraction. In this, what happens is that we keep the screen at finite distance, meaning close to the slit. So this the distance between the slit and the screen is small and it is comparable to the slit dimensions. Then you say you are in the Fresnel regime. Okay, so and in this week, most of the questions are like statement based questions. There are very few numericals, like hardly any numericals that you can see, maybe one or two here and there. So mostly this week assignment is more like statement based questions. Then after this, I will show you some simulations of single slit, double slit, and end slit diffraction pattern. Then you can see basically how the slit width, the slit separation, and the wavelength and the number of slits, how these parameters affect your diffraction pattern. So those simulations will give you some idea. And after that, I will also discuss some previous week assignment questions. And the previous week questions that I've selected are based on coherence. So week 6 was about coherence and Fabry-Perot interferometer. So I have selected only the coherence topic from the last week. Okay, so I think we can get started now with the first question. So the first question is, bending of light as they pass by some object or through an aperture is an example of which phenomenon? So you need to select the phenomenon. Either it is rectilinear motion of light or diffraction of light or refraction of light or all of these. So as always, I will start the poll and all of you please answer in the poll. So it is my request that all of you should try to answer. still some students have not attempted. So I'll give you a few minutes to answer and then we will discuss. So I'm waiting for all students to attempt the poll. So if all of you do not attempt the poll, uh, it makes no sense for me to proceed. So you should all at least try to answer the question before I share the solutions with you. Okay, so I will stop the poll now and share the results of the poll with you. Okay, so those are the results of the poll. Most of you selected the correct option. The correct option is diffraction of light. So one thing to note is that whether you call it diffraction or interference, both these terms are used interchangeably, and the phenomenon is the same. The phenomenon of bending of light as it passes by some objects or through some apertures. And the crucial point is that the dimension of this aperture or the object, the dimension should be of the order of the wavelength, means about the same order of wavelength, maybe a few wavelengths, that should be the order. If the object or the aperture is much larger in comparison to the wavelength, then the effect of this diffraction or interference will not be prominent. And in that regime, you can basically go back to your geometric optics. So geometric optics is valid in the regime where wavelength tends to zero, or you could put it in other words, meaning that the size of the objects is much larger than the wavelength. So in that regime, you can apply geometric optics. But when the size of the object or the aperture is comparable to that of the wavelength, or at least a few multiples of the wavelength, then in that regime you can expect to see some diffraction or interference effect. So the phenomenon is the same. It's bending of light or spreading through some apertures when the sizes are comparable, and whether you call it diffraction or interference, it's used somewhat interchangeably. Okay, so that was the answer. I have seen that some people selected option D. So I'm not sure why you selected those options, but let me clarify once again. So rectilinear motion of light is valid in the case of geometric optics. So whenever you work with geometric optics, the rectilinear motion of light This comes up in geometric optics, where you say that light travels in straight lines. Okay, does someone have a question? Okay, if you do not have any question, then please keep your microphones on mute. Otherwise, if you have some question, feel free to unmute yourself and ask the question right away. Okay, so rectilinear motion of light is for geometric optics, and refraction of light is also bending of light, but it is not bending of light around some object or through some aperture. So there's a difference between refraction and diffraction, and you should be very clear about that. So refraction of light, if I may draw, so you have an interface, uh, and there is medium of refractive index n1 on one side, medium of refractive index n2 on the other side. Okay, and then you have a ray coming in. You have a ray coming in, let's say like this, and based on n1 and n2, let us say n2 is greater than n1, then the ray will bend towards the normal like this. This is for the case when n2 is greater than n1. If n2 is less than n1, then the ray will bend away from the normal. So this is also bending of light. This is also bending of light ray, but this is at an interface. This is whenever there is whenever you have two different media of different refractive indices, and whenever they have a common interface, that's where you will see refraction of light. Whereas diffraction, you would observe, as they say, bending of light through an aperture, meaning you have some aperture, some slit over here, and then light is incident on it. Light is incident on it, and then you will see that light bends or spreads out of this aperture. So this is the phenomenon of diffraction. Whereas the thing that I've drawn below that over here, that's diffraction. And refraction is governed by what we have studied, Snell's law, which says n1 sine theta 1 equals n2 sine theta 2, where theta 1 is this angle of incidence, theta 2 is this angle of refraction. So I hope I have made myself absolutely clear over here, and now you people would not get confused with between what is diffraction and what is refraction. Okay, so we can proceed further. Next question. Diffraction phenomenon can only be explained on the basis of A. Corpuscular model of light, B. Wave model of light, C. Both A and B can explain, or D. None of these. So let me relaunch the poll. Okay, so I have relaunched the poll. Take about a couple of minutes to answer. You have 1 more minute. Okay, I'm glad that all of you have attempted the poll. Let me stop the poll and share the results. It's good to see that this time all of you have attempted the poll. But I'm still waiting for that one question which all of you attempt and all of you get it right as well. That day will be a very happy day for me as well as for all of you. Hello? Yeah, so Binder, do you have a question? So Binder, do you have a question? Uh, Please put it up in the chat box or please unmute yourself. I thought you were trying to ask something. Okay, fine. It seems he doesn't have a question. But anyway, let's come back to our question. So diffraction phenomenon can only be explained uh, on the basis of wave model of light. Option B is the correct option. So most of you got it right, but some of you selected option C. So option C says both A and B, meaning both corpuscular as well as wave model. That is incorrect because corpuscular model of light cannot explain the phenomenon of diffraction. Corpuscular model of light can give you propagation in free space. It can give you reflection. It can give you refraction, but it cannot give you diffraction or interference effects. Whereas the wave model of light, this can explain, basically this corpuscular model is ray model, ray or geometric optics, wherein you assume light to be consisting of rays. Ray is the keyword over here, whereas wave model of light can explain all kinds of interference effects and also propagation in terms of the electromagnetic wave. So this is the regime of wave optics. And then of course you have quantum optics, wherein you assume light to be consisting of photons. Then you have quantum optics, wherein you assume light to be consisting of photons, which is packets of light carrying energy h nu, and then you represent the state by some sort of a wave function, and then you can explain all kinds of effects in the quantum optics domain. So you have this, and then you have a wave function. So that's the domain of quantum optics, which basically includes everything and can explain any effect. But whenever you are in the macroscopic domain, meaning when the size of the objects is much larger compared to the wavelength, you are better off going with ray optics or geometric optics, because that is much simpler to deal with, as opposed to using quantum mechanics to solve those simple problems. So using quantum mechanics would be an overkill for the regime where geometric optics is valid. So that's why these theories exist, because you want to be correct as well as you want to simplify things. So within the approximations of object size being much larger than the wavelength, the geometrical optics theory is valid. Okay, I see there is some problem. My screen has gone away. Let me try to fix that. Okay, I don't understand what's going wrong. Just give me a minute. I will fix this. Yeah, I hope my screen is visible now. Yeah, I'm sorry about that technical glitch. Yeah, so coming back, so these are the different models of light which exists. Ray model or the wave model, or finally the quantum optics domain. Okay, so let us move to the next question. Oh, before that, so when we use the wave model of light, so that explains interference effects, and coming up with the wave model of light was given first by Huygens. He was a Dutch scientist, and some people pronounce it Huygens, but I believe the correct pronunciation uh, in his language would be Huygens. So that's how it's supposed to be pronounced. So corpuscular model of light was given by Newton. So he was the one who propagated this corpuscular theory of light. Of course, there were supporters for this. There was Rene Descartes, who actually came up with this. He was also very prominent with this corpuscular model of light. Then the wave model of light was initially proposed by Huygens. and he tried to propagate this, but he did not get much popularity because Newton was a much more established scientist at that point of time. And then came Fresnel, and then Thomas Young, and all these people uh, performed experiments and promoted the wave model of light. Basically, Thomas Young and Fresnel and Arago, these people performed experiments on interference. So that way they tried to confirm the wave model of light. And then quantum optics, this photon picture uh, was promoted by Einstein, who came up with this idea of a photon and a photon carrying energy of h nu while trying to explain the photoelectric effect. So photoelectric effect was performed, and after that Einstein was trying to give a theory for that, and that's when he came up with the idea of a photon. So this was just some background history about the subject, about the field. And of course, this h over here is Planck's constant, so Planck also had a role in popularizing this model. And this photoelectric effect experiment was performed by Frank and Hertz. So you can just go through some history of science. That is also interesting at times, just to see how the subject and the field has developed over a period of time. Okay, so we will come back to our assignment question. We can't get too much carried away by history because we need to pass our exams as well. So the next question is, Huygens principle is not able to explain the phenomenon of reflection, refraction, diffraction, or all of these. So again, I will relaunch the board. So all of you, please attempt the question. I see still one student has not attempted the board. Okay, so let me stop the poll now and I will share the results of the poll. Okay, so I feel that you people got confused in this question a little bit. The question was Huygens principle is not able to explain. You should look at this word not. I think some people thought that you people maybe missed out this word not, and as a result you selected all of these, but even then the answer would be incorrect. But always try to read the question properly. All these negation type questions, which basically have the word not in them, sometimes people miss that word and end up answering incorrectly, even though they are aware of the concepts. So you should always read the question properly and then attempt the question. The correct answer to this is Huygens principle is not able to explain the phenomenon of diffraction. And why is it so? Let me state the Huygens principle for you, then it will become clear. So the Huygens principle says that every point on a propagating wave front serves as the source of spherical secondary wavelets such that the wavefront at a later time is the envelope of these secondary wavelets. Now, the problem with this Huygens principle is that it does not consider the wavelength, the effect of wavelength. So, as we have studied in this week, the wavelength is very important whenever we are trying to observe diffraction, because the wavelength of light needs to be comparable to the size of the object in order to observe the diffraction effects. If the wavelength is too small, then you do not really observe this effect. Similarly, if the wavelength is much larger compared to the object size, then also it will not see the object. So the wavelength is the crucial aspect, and only when the wavelength is comparable to the size of the objects do you observe the diffraction effect. So, for example, sound waves have wavelength in the orders of like 100 meters. So as a result, you do not very actively observe the interference effect of sound, because in order to observe the interference effect, you would need a size comparable to wavelength, and 100 meters is too long uh, a distance to be able to see any kind of uh, practical or feasible interference effects over that long a distance. So that is important. So whenever if the wavelength is too small, then also it is a problem. If the wavelength is much larger, that is also a problem. So this principle was then modified by other scientists. The crux remained the same, But people then modified this Huygens principle, and that is the basis of our next question, which says that Fresnel modification in Huygens principle was introduced to explain which effect. So I think now all of you, with all that historical background, will be able to get this question right. Let me relaunch the poll. Okay, so I have relaunched the poll. Please answer it. Okay, so you have 1 more minute. I see many students have not attempted the poll this time. Only half of you have attempted. Please do answer the poll. I'll give you an extra minute if you want, but still some students have not answered. Okay, I will stop the poll now. So most of you got it right. The correct answer is A, diffraction, but some people selected reflection. So let me remind you that Huygens principle can explain reflection and refraction perfectly. There was only one small uh, problem, that it could not explain diffraction, but that was fixed by Fresnel, who added an extra term of superposition in the principle uh, to basically explain the diffraction or interference effect as well. So let me state the Huygens-Fresnel principle. This is the modification which allows us to study diffraction effect as well. So it states that every unobstructed point on a wavefront at a given instant serves as a source of spherical secondary wavelets. This part is the same as the Huygens principle. The next sentence is the addition by Fresnel. The amplitude of the optical field at any point beyond it is the superposition. The superposition is the key word over here. Is the superposition of all these secondary wavelets. So this superposition was the addition by Fresnel. So now the Huygens-Fresnel principle can be used to explain all kinds of interference effects. Moving further, the next question we have is on the single slit diffraction experiment. So let me read out the question first. A slit of certain width is used in a single slit experiment. If the slit width is reduced by half of its initial width, then diffraction pattern disappears, or diffraction pattern becomes wider, or diffraction pattern becomes narrower, or the diffraction pattern remains the same. I will relaunch the poll for you. Please attempt the poll. We will then see some simulations of the single slit so that these concepts become clearer to you.
Ma'am, I have a question.
Yeah, go ahead.
Yes, ma'am. Ma'am, in the previous questions, Huygens principle on modification over Huygens principle, and in the statement, the amplitude of the electric field means optical field means the electric field vector of the amplitude of
Yes,
the electric field vector.
amplitude of the electric field vector. So whenever you are doing superposition, you
Yes,
always
ma'am.
talk about the amplitude of the electric field vector. You never talk about the superposition of the intensities. So superposition is always in the amplitude domain, amplitude of the electric field. And to get the intensity, then you do the mod squared of this electric field.
Yes. Okay, ma'am.
Yeah. Yeah, good to see that people are asking questions. Okay, very few people have answered the poll this time. Please attempt the poll. Only 50% of you have answered the poll. Take about a minute more, but please all of you attempt the poll. Okay, so I will stop the poll now. Uh, Unfortunately, none of you have got this question right. So let me share the results of the poll. So I was waiting to see everyone get a question right, but instead I have come across a question which none of you have got it right. But anyway, that means that my simulations would probably help you. The answer to this question is option B. The diffraction pattern becomes wider. So if you reduce the slit width, then the diffraction pattern becomes wider. So if my slit width goes down, then pattern becomes wider. Uh, on the contrary, if my slit width increases, then my pattern becomes narrower. So that's the inverse relation between the aperture size and the diffraction pattern. So in the simulations, I will show you. So in the simulation, I will show you the diffraction pattern as a variation with width as well as its variation with wavelength. And let me write down the intensity for the single slit diffraction pattern. So single slit diffraction pattern is given as follows. Where beta is the following. B is the width and theta is the angle on the screen. Meaning this is the angle of the point. So if this is my slit, let me draw a quick schematic. If this is my slit, this is my screen. Then if this is the point, then theta is this angle it makes with the horizontal. This is theta. and this slit width is B. Okay, so that's that. So let me now show you some simulations. Let me stop sharing the poll and let me go to my Mathematica screen. Okay, wait, something went wrong. Just give me a second. I'm trying to share my Mathematica screen. Yeah, so now my screen is visible. Let me go to the single slit. So this first plot out here, this is for the single slit. Let me write down. So this is for the single slit pattern. And let me run this. So this is what you see. Single slit pattern. This is slit width is very small and wavelength is of the same order. Now if I increase my slit width slightly, you see that the pattern becomes narrower. As I'm increasing my slit width, the pattern becomes narrower and narrower. You see that? Keep on increasing the slit width, pattern becomes narrower. If I decrease the slit width, then pattern becomes broader. And you see these side lobes appearing over here. So this is a plot of the intensity versus theta. So on the x-axis, I'm plotting theta. Okay. And now let me see what happens with wavelength. So if I increase my wavelength, you see, if I keep on increasing my wavelength, if my wavelength becomes extremely large in comparison to the slit dimensions, then you don't see any pattern. You just see normal uniform illumination. Similarly, if I keep my wavelength very small and if I increase my slit width, keep on increasing, you see that the pattern becomes narrower and narrower and very, very narrow. And almost just in the center, there is some peak, and beyond that, there is nothing. So, this is the variation with respect to uh, wavelength as well as slit width. So, important thing to notice, if you decrease the slit width, then pattern will become broader. If you increase the slit width, then pattern will become narrower. One more thing we can try is, let me try it over here right now, is instead of plotting it with respect to theta, I can plot it with respect to distance on the screen. Let me try. Okay, let's try this. So you see, as I'm increasing my slit width, the pattern becomes narrower and narrower and narrower. See, this is much better actually. And if I increase the wavelength, then the pattern becomes broader and broader and broader. Okay. And if I decrease my slit width, then pattern becomes broader. And on top of it, if I increase the wavelength, even broader. And if the slit width is very small and wavelength is very large, then you see almost uniform illumination. Let me reduce this distance slightly. See, an important thing to notice that these side lobes are very faint in comparison to the central lobe. Let me keep it at here. So here you can see 1, 2, 3 side lobes and maybe the fourth one coming up. But you see that these side lobes are very, the peak height of these side lobes are very small in comparison to the peak height of the central lobe. And the first lobe is still somewhat there, beyond that even smaller height. So as a result, when you perform experiments, it is very difficult to observe these side lobes beyond 1 or 2 side lobes. Okay, so these were the simulations. We can come back. I hope now this helps. So once again, I will reiterate this effect that if you increase the slit width, then pattern becomes narrower. If you decrease the slit width, then pattern becomes broader. Maybe I could play this as a video. Let me slow down the video a little bit. See, as slit width is increasing, your pattern is becoming narrower. With wavelength, the reverse effect happens. With wavelength, as the wavelength increases, your pattern becomes broader. So let me keep the slit width at the maximum and let me now play the video for the wavelength. So see, as wavelength is increasing, pattern is becoming broader and broader and broader. Even broader. Okay, let me stop it now. So let us come back to our question. So I hope this is clear to you now. And please remember this inverse relation between the aperture size and the pattern. So there is always this inverse relation. So aperture size decreases implies that the pattern size increases. So this you should always keep in your mind. And with this in mind, let us move on. The next question, in the Fraunhofer diffraction regime, the effective distance of source and screen from the aperture would be A, double of the wavelength of light, or B, half of the wavelength of light, or C, infinite, or D, none of these. Once again, I will launch the poll. This I had mentioned in the very beginning as well. Before we started with today's assignment problems, I had given an overview, so you all should get it right. Still one student has not answered. Please answer the poll. You have about a minute more. Okay, so I will stop the poll now. Most of you got it right. The correct option is infinite. So Fraunhofer diffraction regime, both the source and the screen are at infinite distance from the slit, and this is what I wrote in the beginning as well. So Fraunhofer is far field regime. Far field regime meaning screen and source both are at infinite distances. And how could you achieve that? So, and by the way, infinite distance of the source would mean that you have effectively plane waves hitting the slit. And how would you achieve that infinite distance? You could do by either keeping it very far away from the slit. When I say very far, that means the distance between the slit and the screen and the slit and the source is much, much larger in comparison to the dimension of the slit. That is one way. Another way is to keep the source at the focal plane of a lens. So you have the source. So it is at the focal plane. So if you have this is focal plane, this is at F, then you have parallel rays coming out. This then hits the slit. So you have the slit over here. And then after the slit, again, you place a lens and then keep the screen at the focal plane. So this is also F. So this is one way you can achieve this infinite distance of the source and the screen from the slit plane. Uh, other thing that you can do is just keep these distances very large, like this, in comparison to the slit width. So these are two ways in which you can uh, basically achieve the Fraunhofer regime, Fraunhofer diffraction pattern. In the Fresnel regime, we are in the near field domain. That means the distances between the slit and the screen is small. When I say small, it means that the distance is comparable to the dimension of the slit. So I see someone has raised their hand. So could you unmute and ask or put your question in the chat
Ma'am,
box?
ma'am,
Yeah,
yes, ma'am. I have a question.
yeah.
I have been reading in the chat box Fresnel biprism. Could I use the Fresnel biprism method to make a sources infinite distance?
No, not really. Because that is also not making it at infinite distance, because that is keeping your in the Fresnel biprism, your the virtual sources that are created are at the same distance as your actual source that you have. It's in the same plane. The plane does
Yes, ma'am.
not change.
Okay,
So
okay,
yeah, so Fresnel biprism, if I could draw it over here, let's say, let me see if I have some space. So in the Fresnel biprism that you have a setup like this, then you have a source over here, and the virtual sources that are created are in the same plane as this original source. So if this is your S, this is your virtual source S1, this is your virtual source S2. So these S1, S2 are created in the same place as your source S. So
okay,
if you take your source very far away, like a kilometer away, means that is too much saying. Let's say 1 meter away, that itself is infinity in terms of physics. 1 meter or 2 meter away from your slit plane, then that is infinity. But that is as good as using this setup where you have just one source and one slit. So yeah, good question. Good that you are trying to think of different ways. But as of now, that these are the two ways. First one is using lens, and second one is just increasing the distances much larger than the slit dimension.
okay, okay.
Okay, yeah, very good. Okay, so next question. This is on double slit. And for this also, I have some simulation planned. But before that, let us look at the question. In double slit diffraction, width of each slit is increased by the same amount, keeping the center to center separation between the slits constant. Number of fringes within the central diffraction peak will A increase, B decrease, C remain the same, or D none of the above. So I will relaunch the board. So please attempt the board. Up until now, very few people have attempted. All of you, please attempt. Okay, so I will stop the poll now. So it seems most of you have got this one wrong, which means my simulations would be even more beneficial to all of you. The correct answer is that the number of fringes within the central diffraction peak will decrease. So, uh, once again, the simulation that I will show, this will be as a function of slit width, the slit separation, and the wavelength. So this slit separation is nothing but this center to center separation that they have written over here. That is the slit separation. And what this question is saying that you have a case wherein you have these slits and their center to center separation is kept constant, and what you are doing is you are doubling the width of these slits. Okay, my slits now look like square. Okay, somewhat like this. So this is what is happening. So now when your slit width is increasing, as I showed in the single slit uh, simulation, that if the aperture's size increases, then your pattern will become narrower. So slit width is increasing. That means the central maximum will reduce in size. The diffraction peak would reduce in size. As a result, there will be fewer interference maxima coming inside that. So let me write down the expression and then it will become clearer to you. So this is the expression for the double slit, the intensity for the double slit diffraction. Here beta, as before, is kb by 2 sine theta and alpha is ka by 2 sine theta, where b is slit width and a is slit separation, the center to center separation. Okay, and notice that if my b goes to 0, then I'm left with 4 I naught cos squared alpha, which is nothing but Young's double slit interference experiment. So in Young's double slit experiment, we had assumed that the slit width is infinitesimally small. So this is what you get when you plug in the value of slit width equal to 0. You uh, obtain the Young's double slit interference experiment. And on the other hand, if you make your slit separation equals to 0, then you obtain the single slit. Then you obtain this sine beta over beta squared, apart from that extra 4 I naught term. But this functional form is same as your single slit diffraction pattern. So this double slit diffraction pattern is basically a combination of your single slit diffraction and Young's double slit interference. It's a product of those two. So let us see in the simulations. Yeah. So here I have the simulations. Let me write down double slit for you. This is for double slit. So let us now change the slit width and separation and see what happens. So first, let me increase the wavelength a little bit, or let me increase the slit width. So I'm increasing the slit width. As you see that the diffraction pattern is becoming narrower and narrower. Now let me increase the wavelength. So it will become broader and broader. Let's keep it at here. Okay. Now notice what happens when I increase this slit separation. See, I'm increasing the slit separation, then it becomes narrower and narrower. And these additional fringes start appearing. See this finer additional fringes from the Young's double slit interference fringes. So when I increase the slit separation, then the interference fringes become more closely, like the spacing between the interference fringes reduces. So as a result, you see more of these interference fringes within that diffraction peak. Now, as the question said, that if you increase the, let us see at this point how many fringes are there. I see one central fringe, 2, 3, 4, 5, 6. So 6 fringes I see within the central peak. Okay. I'm counting towards the right side. So central is 1, then 2, then 3, then 4, then 5, and then 6. Now if I increase the slit width, see these number of fringes reduce. Now I can only see 1, 2, and 3, and maybe this fourth one tiny. If I increase even more, see even less and less. Now only 3 fringes I can see. So that was what the question was. If you increase the slit width, keeping the separation constant, then the number of fringes within the central diffraction peak will decrease. Now, what do we mean by this central diffraction peak? So let me plot that within this for you. So, okay, let me do it separately. Let me copy this. I will plot the diffraction peak as well as this single, as well as this double slit diffraction pattern. Let me plot the single slit pattern. Now you will see both of them. Oh, oops, there seems to be some error. What is the error? Okay, there is some bracket problem. Oh, sorry, I need to use curly braces. Now it should work. Yeah, there you go. So, let me keep the same values as above. So this needs to be 0.64. This needs to be 7.14. And this needs to be 2.48. Okay. See this. This orange one is the single slit diffraction. And the blue one is the total double slit interference pattern. So now you see, as I'm changing this, see that? What is happening? So if I'm increasing the slit width, then the number of fringes within that single slit diffraction peak reduces. One more thing I can do for you is plot even the Young's double slit. sorry, Young's double slit interference I will plot. This is this cosine term over here. Okay, this is becoming too much complicated, I think, because too many plots are there in the same thing. Yeah, I guess this is becoming complicated, but what I was trying to show is that these blue lines, these small fringes are equally spaced because of this Young's double slit experiment pattern. What I can do is I can do one more thing. Instead of plotting with theta, I can plot it versus y, or let me make it in a new plot. So let this one remain as it is. Let me make a new plot. Yeah, does someone have a doubt? Uh, Someone's mic is unmute. If you don't have a doubt, please mute your mic. Yeah.
ऐसा मैं एड्रेस भेज रहा हूँ वो बैंड भिजवा दो आप बताओ मैं एड्रेस भेज रहा हूँ बैंड भिजवा दो कितना खर्चा आएगा उसमें
Excuse me, like if you do not have a question, please keep
नहीं
yourself
अगर
on
100
mute.
150 अगर 100 150 तक आता है ठीक
Okay,
है
wait,
उसके
let
नीचे
me
5,000
first
पाँच
mute
सौ
this
लगेगा
guy. So Sobinder, if you don't have a question, please keep yourself
ठीक है
on mute,
हाँ ठीक है चलो
or I'll mute you. Either way. Okay, yeah. So now this is much better. So, and in this I can then add the Young's double slit part, which is this part. Cool. So now let us see. We will increase the wavelength, increase the slit width. See, the green line is the Young's double slit fringes, and you see perfect cosine fringes equally spaced. Now I will increase the slit width, and then you see the orange is the envelope of the single slit diffraction. Okay, this point it looks good. Okay, this place it looks good. Okay, so now you see this orange line is the single slit diffraction. You see the central single slit diffraction peak and then one side peak. Okay, these green lines are for the Young's double slit interference experiment, and you have seen that these are equally spaced cosine fringes. And this blue line is a product of the orange and the green. So what you see is, you see for the blue line, as we saw above, as we saw here, as you saw over here, you see that the orange line is the envelope of the blue curve. So orange curve is the envelope of the blue curve. You see this? So peak of the blue coincides with this orange, and these interference fringes are at exactly the same location as the Young's double slit experiment. So with this, you can actually see what is happening. So this double slit experiment is nothing but a product of the single slit diffraction times the Young's double slit interference experiment. And this is what you get. Okay, so I can come back. Okay, there is some technical glitch again. I don't know why my tablet got disconnected. So I'll come back to this. Okay, so let me fix my tablet. Yeah, that's it. So now you see what is happening with the help of these simulations. So I hope it is clear. Since most of you got it wrong, I thought the simulation would help all of you. That's why I spent a little bit more time with the simulation. Next question is also on double slit diffraction. In double slit diffraction, center to center separation between slits is increased, keeping the slit width constant. Number of fringes within the central diffraction peak will A increase, B decrease, C remain same, D none of the above. So now that you have seen the simulations, I hope all of you should get it right. So let me restart the poll. Okay, please answer the poll.
Ma'am, ma'am,
Yes,
ma'am, here the what is the center to center separation? That means
that means, as I mentioned above, that means this slit separation. Slit separation
okay,
meaning this separation.
okay. Probably I have choose the wrong answer.
No worries, we will revise it over and over again. That is not a problem. Okay, so I will stop the poll now and let me share the results. Okay, so let me now tell you the correct answer. Oh, here there is a complete range of answers. People have selected all the options. So the correct option is option A, increase. And we will go back to the simulations and see this once again. But let me just give you some intuition as to what is happening. So so there are two effects as I mentioned. First is the single slit diffraction. This effect times the Young's double slit gives you the double slit diffraction. So you have to keep both these two effects in your mind. And the important another important thing to keep in mind is that the aperture size and the pattern have an inverse relation, meaning aperture size decreases, so pattern size increases. Now, we have seen that the single slit, let me use, let's say, blue color for single slit diffraction. So single slit diffraction pattern looks somewhat like this. Very broad and high peak central maximum and then very small other lobes. That's single slit. And Young's double slit is like this, equally spaced cosine fringes. Okay, and the single slit diffraction pattern is governed by the slit width B, and the Young's double slit is controlled by the slit separation A. So if you increase the slit separation, then the Young's double slit interference pattern will become narrower, means more and more fringes will start coming in. So the question says, if the center to center separation is increased, so when I say center to center separation increasing, that means slit separation A increases. That means in the Young's double slit interference, the slit separation increases. So when in Young's double slit, if you increase the slit separation, then your fringes come closer together. So if the fringes come closer together, you will be able to fit more of these fringes within this central lobe. So this is the central lobe. You will be able to fit these many fringes. And if you increase the separation, that means more closely spaced fringes, let's say even more closely spaced fringes, then you will be able to fit a lot more. So you will be able to fit, let's say, this 1, 2, 3, 4, 5, 6, roughly 6 or 7 of these. Whereas earlier you were able to fit, let's say, 3 of these. So this is when your slit separation decreases. Similarly, if you increase your slit width, if I increase my slit width, if my B increases, then my diffraction pattern itself will become narrower. And then I will be able to fit less number of these Young's double slit fringes within that. So that was the whole point of that simulation. So I hope this intuition is makes things much more clearer for you, that double slit diffraction pattern is nothing but single slit diffraction pattern times the Young's double slit interference. And each of these, oh no, today my connection is little bit choppy. Let me connect once again. Yeah, we're back again. So please keep in mind that these are two independent effects, single slit diffraction and Young's double slit interference. And these two independent effects combine to give you the resultant double slit diffraction. And once again, let me go back to my Mathematica and repeat this for you. This time the question says that slit width is kept constant. So slit width means B is constant, and then we are increasing center to center separation, meaning A. So if I increase A, you see number of these fringes increases. So let me start with some very small value of A. Very small value of A. Okay. Here you see only one blue peak is there within that orange peak. If I increase my A, you see now 3 blue peaks are there within that orange peak. So if I increase my A even further, now you see 5 blue peaks are there within the orange peak. Keep on increasing. You see now 7, now maybe 9. See, I'm keeping on increasing, now 11, now 13. Keep on increasing the slit separation. You see more and more of these uh, Young's fringes within the diffraction peak. Okay, so I hope that is clear. Let's come back. Two more questions to go. A slit of width 0.2 mm is illuminated by the light of the wavelength 530 nanometers. The angle corresponding to first minima would be, you need to select the angle corresponding to the first minimum for the single slit diffraction pattern of the given width and given wavelength. So I will relaunch the board. Okay, so someone in the YouTube chat box is asking for textbook. So I have told this in previous classes as well. So a good textbook is Optics by Ajoy Ghatak. And another textbook that you can use is Optics by Eugene Hecht. These are two good standard texts that you have. And both these texts basically cover all the aspects of interference and diffraction and all these effects that we are discussing in this course. So I hope it answers the question. So this was the question on the YouTube chat box. Okay, so I will stop the poll now and discuss the answer. So the single slit diffraction pattern intensity is given as follows. Where my beta is kb by 2 sine theta. So the minima of this will minima occurs whenever sine beta goes to 0, and sine beta goes to 0 for beta equals plus minus pi, plus minus 2 pi, plus minus 3 pi, etc. Note that we are not including beta equal to 0 because beta equal to 0 is the central peak that corresponds to the central maxima. And this happens because limit of beta tending to 0 sine beta over beta equals 1. This limit you can find by using what is known as the L'Hopital's rule. So using the L'Hopital's rule, you can find out this limit. What this rule says that you differentiate the numerator and the denominator and then apply the limit. So this is same as limit beta tending to 0. Derivative of sine beta is nothing but cos beta. And derivative of beta is nothing but 1. And now when you put beta equal to 0, you get 1. So using L'Hopital's rule, we get this limit. And that's why we exclude beta equal to 0 because that corresponds to the central maximum. So first minima will occur at beta equals pi. That's the first minima. Either plus pi or minus pi you can use. The second minima would be at plus minus 2 pi, but we don't want to look at that. So beta equals pi. Now this implies beta is what? Kb by 2 sine theta. Kb by 2 sine theta equals pi, which implies sine theta is 2 pi over kb. Now k is nothing but 2 pi by lambda. So this is 2 pi over 2 pi by lambda b. So 2 pi gets cancelled. You get lambda over b. That is sine theta. So this means sine theta equals lambda over b, and lambda is given as 530 nanometers. This is 530 nanometers divided by b is given as 0.2 millimeters. So this is 265 into 10 to the power minus 9 from the nanometers into 10 to the power 4 from this millimeter and 0.2. So this is 2.65 into 10 to the power minus 3, and this is approximately equal to theta. So when theta is small, so for small angle, sine theta is approximately equal to theta. So using that, we approximate this to be equal to theta, and that gives us theta as 2.65 into 10 to the power minus 3. So option A is the correct option. Surprisingly, again, in this, none of you got the correct answer. All of you have selected the incorrect options. But I hope now this makes it clear. Finally, we have the last question for this week. Let me stop the poll and relaunch it. So the question is, missing order occurs in a double slit diffraction experiment when option A, interference maximum and diffraction minimum corresponds to the same angular position, or B, interference maximum and diffraction maximum corresponds to the same angular position, or interference minimum and diffraction minimum correspond to same angular position, or interference minimum and diffraction maximum correspond to same angular position. Okay, I'll give you a minute. Okay, so I'll stop the poll now. The correct option in this is option A. Missing order occurs when the interference maximum and diffraction minimum correspond to the same angular position. What this means is, so this is your Young's double slit, which is the interference maxima, and this is your single slit diffraction. Now, if you look at it, okay, let me little bit. Okay, yeah. Now, if you look at it, this interference maximum coincides with this diffraction minimum. So this will lead to a missing order. You will not see this maximum. You would only see this central peak right here, and then a missing order because this is missing, and then when you come here you will see one peak due to this, like this you will see. So this order basically gets skipped, so that is the missing order. So that's the end of the assignment questions. I have one more simulation planned, so maybe I'll just give a quick overview. So we have already run out of time, so maybe in 2-3 minutes I'll just show you what this simulation is. This is for multiple slit diffraction. Okay, so in this week we saw single slit, double slit, and multiple slit diffraction. Now, multiple slit diffraction, the intensity is given as follows. Here, as always, beta is kb by 2 sine theta and alpha is ka by 2 sine theta, and b is the width, a is the separation, and n is the number of slits. Okay, so quickly I will just show you the pattern. So here it is. This is the double slit pattern. Maybe I'll write it below this time. Not the double slit, sorry. This is N slit pattern. And what you see, the difference between the double slit and the N slit. So here, this is the double slit pattern for the parameters B, A and lambda given over here. For the same parameters B, A and lambda, I have now the N slit where N is 10 over here. What you see, the difference is that each of these interference peaks becomes sharper and narrower. So that's the difference. If I reduce the number of slits, you see that the sharpness of the fringes decreases, and see at 2 it is the same. And if you increase, then you see sharpness keeps on increasing of these interference fringes. So that's the difference between N slit and double slit. The sharpness of the interference fringes increases. Okay, so that brings us to the end of this session. And for those of you who joined late, let me share the link to the YouTube channel once again.
Ma'am,
Yes?
ma'am, in last 3 weeks, I have had an exam. For that reason, I could not join. I have seen the YouTube lectures in later.
Okay, fine. Not a problem.
Yes, ma'am.
Yeah, okay.
And ma'am, could I share? I want to say one thing.
Yeah.
Yes, ma'am. Ma'am, recently, at IIT Kanpur, Aditya support self-feed workshop will take place in September last, right?
Okay.
Yeah. Yes, ma'am. I have got selected for that workshop.
Oh, that's very nice. Very nice. Congratulations.
I have got selected, and most probably I'll go 28 September.
Okay, so you are visiting IIT Kanpur towards the end of September, is that right?
Yes, ma'am. Yes, ma'am.
Okay, that is very good. So once you are here, then we can maybe meet sometime.
Please, ma'am, again, I could not hear.
Yeah, so that's very good. So once you come to Kanpur, then maybe we can meet for some time.
Okay, ma'am. Yes, ma'am. Sure, ma'am.
Yeah. So yeah, good to know. So when is that workshop? I forgot the dates.
Yes, ma'am. The workshop will goes from 29 September to 1st October, 29, 30, and
Oh,
October
that's the
1st.
that's the Friday, Saturday, Sunday, right?
Yes, ma'am. Yes, ma'am. And I will go by 28th morning, 28th morning or daytime, and I will continue for 2nd October daytime
Okay,
because
fine.
the one day ahead and one day after the free lodging and boarding also provided.
Okay, very good. Yeah, so you will be kept in a hostel over here. So there are many hostels. So you will be kept in some one of the boys' hostels. So
Yes, ma'am.
yeah, very good. If you want any help, you could then drop me an email and yeah, we can fix up a meeting time. So are you there on LinkedIn?
Yes, ma'am.
Are you there on LinkedIn?
Yes, ma'am. I am also in LinkedIn.
Okay, so you can send me a connection request on LinkedIn and then we
Yes,
can
ma'am.
connect and meet.
Okay, okay, ma'am. Okay, ma'am. Sure, ma'am. I'll surely put you the information according to that place of
Yes.
meet.
Yeah, sure.
Okay, thank you, ma'am.
Yeah, very good. Good to know that.
Thank you.
Okay. Bye bye. Yeah, hi Subhinder. Do you have a question? You are unmuting yourself but not asking anything relevant. You're just some background noise is coming and then you're putting some things in the chat box.
Good afternoon, ma'am.
Yeah, hi Subhinder.
Can you provide me video recording of this lecture?
Yeah, so the recording of this lecture is on the YouTube link. I've shared the link to the YouTube channel in the chat box. So you can get the recording on that YouTube channel.
Okay, thank you.
Okay, great. So bye bye.